Welcome to the second part of our introduction to modeling biological and ecological systems. In this module, we will be diving a little deeper into our examination of models and modeling approaches. We will also continue to define terms related to modeling and discuss characteristics of different approaches. We will discuss some of the advantages and disadvantages of modeling, and finally, we will describe some criteria for documenting models that will be used in our first homework assignment. Upon completing this module, you should be able to 1. Identify different types of models and describe key characteristics of different model types. 2. Understand how to select an appropriate choice of models. 3. Be aware of some of the advantages and disadvantages of developing and using models. And 4. Identify factors to consider when documenting a model. In the previous module, we focused on models as simplifications of reality and developed some approaches for representing these simplifications diagrammatically. This can be a useful exercise for clarifying thinking and communicating your conceptualizations to others. Conceptual models are often expressed as diagrammatic models. These are sometimes referred to as systems diagrams or stock and flow diagrams and can be useful to establish what variables are important to consider in a system and how they relate to other variables in the system, and communicating the basic elements and structure of a model in a non-mathematical way. Another way to characterize models is whether they describe data or describe a system. Data-driven models, termed empirical or regression or statistical models, are used to fit a function to a set of data. They do not necessarily represent actual processes in a system, but instead seek to identify a functional form that relates one response variable to one or more explanatory variables based on fitting the functional form to an observed dataset. Empirical models are appropriate for situations where you have lots of data, but not necessarily a lot of understanding of or need for capturing the underlying processes that contribute to a system's behavior. Or if you are simply trying to quantify the relationship between one variable and another as easily as possible. In the example shown here, we are modeling crop yield as a function of water use, expressed as evapotranspiration over a growing season. We estimate a simple line function based on the data. No underlying mechanism is contemplated in this model, but a relationship between these variables is established. In contrast, mechanistic models, sometimes referred to as process or theoretical models, focus on describing fundamental processes controlling system behavior. While typically informed by data, a mechanistic model tries to capture mathematical descriptions of these processes first and foremost, using data to parameterize the model if needed. At their most extreme, mechanistic models require no data, as they fully capture the processes that drive system behavior. Mechanistic models are useful when data is limited, or when a model that captures underlying processes is needed. They tend to be more complex and therefore more expensive, difficult to develop, but are generally more flexible in application because they are not so tied to specific datasets, and because they are focused on representing process mechanisms, not just fitting data. A typical example of a mechanistic model is a hydrologic model that incorporates hydrologic process descriptions, say canopy interception, surface runoff, or in-stream routing, to estimate water availability at various points in a watershed. In reality, many models incorporate aspects of both empirical and mechanistic modeling approaches, capturing some representation of underlying processes while calibrating the model to specific datasets for specific situations. Another important way to classify models is whether they capture variability in the system or not. For questions and systems for which variability is an important aspect, we will likely want to incorporate descriptions of that variability into the model. Examples might include, what is the likelihood that it will rain tomorrow? Or, how frequently can we expect a river to flood? Notice the use of terms that are inherently probabilistic in nature, like likelihood or frequency, in these questions. This has an important implication because inputs into these models are variable. These models, referred to as stochastic models, must be run many times to generate many outputs, which in turn are fitted to a statistical distribution. We will examine this process, termed Monte Carlo simulation, later in the course. In contrast, deterministic models don't attempt to capture variability. Running a deterministic model multiple times for a given set of inputs will always result in the same output, whereas running a stochastic model with a given set of inputs will result in a distribution of different outputs. Because stochastic models require more effort to develop and run, the variability in inputs, as well as the variability in outputs, has to be quantified, and the model needs to be run many times to be useful. Most models are of the deterministic kind. However, if your question explicitly deals with variability, you should be thinking in terms of a stochastic model. Yet another way of classifying models relates to how the resulting mathematical representation is solved. For simpler models, we can often find a closed form or analytical solution that allows us to directly solve for the response variable. These are convenient and efficient ways to solve a model. However, there is a large class of models, particularly more mechanistically oriented models, for which a mathematical equations in the model cannot be directly solved. These are termed simulation models. This is generally not a significant problem, as a large variety of numerical methods exist for solving these equations through indirect or approximate, but generally extremely accurate means. We will be discussing some of these techniques later in the course. The availability of these techniques means that model equations generally do not have to be constrained by their solvability, but instead can focus on providing an adequate representation of the system of interest, with the generally valid assumption that the resulting equations can be readily solved using numerical methods implemented in a computer program. Finally, I'll mention one other type of model, a physical model of a real system. These models attempt to reproduce a system using a scaled-down version of that system. One example is a wind tunnel. It tries to reproduce the effect of a wind profile moving through a high-speed air current. A second example, depicted in the figure shown here, is part of an Army Corps of Engineering physical model of the Mississippi River Basin. In this case, the physical model captures the topography and drainage characteristics of the basin through appropriate scaling factors and allows for the simulation of rainfall events and their impact on hydrology, and specifically flooding, throughout the system by observing the physical response when water is applied to that physical model. Can you think of any other examples of such a model? So, what's the right modeling approach to adopt for a given situation? As with many things, the answer is, it depends. In general, though, keep the following guidelines in mind. As always, the first step in any modeling effort is to start with a question you are trying to address about a system. This helps clarify what the model needs to consider and the types of outputs the model needs to produce. It can also help to establish what variables your model needs to consider. Next, you will need to identify a modeling approach to use. This will largely depend on 1. How much data you have available to you to develop your model, and 2. How complex your system is, and 3. How much time and effort you have available to develop your model. First, consider how much data you have to work with, and how much understanding you have of the fundamental processes controlling the system. If you have relevant data sets relating described variables of interest, and just need to characterize the mathematical relationship between these variables, an empirical modeling approach is appropriate and is generally relatively easy to develop. Empirical models generally rely on fitting data to a predetermined mathematical equation, a process known as regression. Regression finds the best fit parameters for a model using the data sets provided to the regression procedure. Alternatively, if your system is more complex, the data on your system is scarce, consider developing a mechanistic model that focuses on describing the fundamental processes that drive system behavior. A mechanistic, or process model, requires understanding of the nature of the phenomena being modeled, and captures that understanding in mathematical forms. These models tend to be more complex and more difficult and time-consuming to develop and use, but can result in more robust representations that can generally be applied to a larger variety of systems, since these models attempt to capture what is really going on in a system, as opposed to empirical models that focus on representing a particular data set. Another important consideration is whether you need to capture variability in your model. Models that incorporate variability are termed stochastic models. Models that don't are termed deterministic models. Generally, stochastic models are mechanistic, but this is not a requirement. Empirical models can capture stochasticity in a system as well, but this is less common. In practice, many models are blends of mechanistic and empirical approaches. They attempt to capture the key fundamental processes controlling a system, but may rely on regression approaches for tuning the model to a particular location or situation. Let's do a quick mental exercise. Suppose you want to develop a simple model estimating a treatment efficiency of a constructed wetland designed to absorb nutrients from paper mill wastewater at a particular location in Oregon based on nutrient loading levels into the system. For the system in question, let's further assume you collected data over several seasons that relate wastewater loadings, the flow rate multiplied by nutrient concentration, to treatment efficiency. What type of modeling approach would you take to develop a design equation for this system? In this case, one could consider both a more empirical approach or a more mechanistic approach. An empirical approach is probably more relevant to this situation, since the goal of the model is to develop a simple relationship between treatment efficiency and nutrient loading, and have ample data to do so. An empirical model would be easy to develop from the data. However, because the model isn't capturing fundamental processes describing how nutrients are taken up and transformed by the biological components of the system, an empirical model will not be generalizable as a more mechanistic model might be. Let's do a second example. Here, we want to understand how water moves through a landscape, starting with precipitation in the form of rain or snow, and tracks the transport of this water as it moves through the landscape. This is a complex process reliant on many landscape characteristics, for example, leaf canopy structure, hydraulic conductivity, topography, and others. But these are fairly well understood phenomena. While you have some data on the system, you typically would not have data on all important processes in the system. Further, you'd like the model to be broadly applicable to other watersheds controlled by similar processes. What would be an appropriate modeling approach in this case? In this case, a mechanistic model may be more appropriate than a strictly empirical approach. Since the system is complex, your data is somewhat limited relative to the complexity of the system, and a goal is to have a model more generally applicable to a range of similar systems. A significant downside is that because of the complexity of this system, a mechanistic model is likely to be significantly more expensive to develop and operate, but will generally provide a significantly more robust representation of the real system being analyzed. An example of a model commonly used for this application is the SWOT model. SWOT is short for Soil Water Assessment Tool. Look it up. What types of applications has the SWOT model been used for? Let's talk about what you can do with models. In general, models are used for 5 tasks. First, we use models to communicate our understanding of the relationships between variables in a system, or how a system operates. They allow us to express useful simplifications of reality and communicate these simplifications to others. Second, the process of modeling can improve our understanding of a system, identify gaps in knowledge, and provide insights into emerging properties of a system that are not necessarily obvious. Third, models allow us to test hypotheses about how a system works and predict the behavior of the system in response to new stimuli or operating conditions. By capturing current understanding of the relationships controlling system behavior in a mathematical model, and then comparing modeled results to the real system behavior, we can determine if our understanding of how the system works is consistent with reality. Further, models allow us to explore systems that we cannot or do not want to or are too expensive to create in the real world. There are many examples of this. Can you think of any? Some examples include understanding the effects of elevated CO2 emissions on climate, damage from nuclear weapons explosions or pest disease outbreaks, or gene spread from genetically modified organisms introduced into the environment. These are experiments we either can't easily do, for example, global effects of elevated CO2 on hurricane intensity, or don't necessarily want to do, e.g., nuclear weapons tests. Finally, models allow us to optimize system performance through application of mathematical optimization algorithms operating on our model. There are also significant pitfalls associated with models and modeling that you need to be aware of and keep in the back of your mind when you are dealing with a model. First, mathematical models can be intimidating for non-modelers, particularly those that apply to complex systems. Although a real benefit of a mathematical representation of reality is the clarity the language of mathematics imposes, for the mathematically challenged, this can be a barrier to understanding. Second, all models contain assumptions, many of which are often hidden. You should always be aware of the assumptions embedded in a model and always document those assumptions when you describe the model. Third, model results can be too easily believed. You should always approach a model and results produced by a model skeptically. Assume that it is wrong unless you have evidence to believe otherwise. Be aware of the assumptions contained in a model when interpreting model results. And finally, models can be expensive and time-consuming to develop, particularly those dealing with more complex systems. Unfortunately, many systems, particularly ecological systems, are complex. However, models give us useful tools to understand this complexity and better design and optimize these systems. Models are useful for exploring many questions in systems, but not all. The figure depicted here puts appropriate use of models in the context of, first, the degree of understanding of fundamental system processes on the x-axis in the chart shown here, and second, data quality and availability on the y-axis. Towards the lower left-hand of the corner of the figure, models have limited utility. You really need to have either a significant amount of good data about a system or a significant understanding of the process controlling a system, or both, for a modeling effort to be effective. As data quality and quantity increase, empirical models become useful tools for gaining insight into a system and recommending management actions. As the understanding of the fundamental processes controlling a system increases, mechanistic models can become valuable tools for gaining insight, recommending action, and designing complex systems. Think of a system you might want to model. Where would it fit on this diagram? What type of modeling approach might you take to address this system? Why? Let's use ecosystems as an example. For many ecosystems, we have collected considerable amounts of data. We have some, but certainly not complete, understanding of how these systems work. We can infer that empirical or partially mechanistic models might be appropriate. Astrophysics, in contrast, is very well understood. Even though we may not have large quantities of data, we can use a mechanistic model, well grounded in theory, to accurately predict, for example, how these systems will behave, to the point where we can design spacecraft to intercept far distant planets. Economics, on the other hand, is a field where a fair amount of data is available, but mechanistic understanding of how economic systems works is still lacking. Economic models, therefore, may be best used to gain insights, but should be used with significant skepticism when designing an economic system. Where do you think some systems of interest to you might lie on this chart? Finally, we close this module with some guidelines developed by Scott Overton, an ecologically oriented statistician from Oregon State University, to describe a model. He describes several aspects to consider when documenting a model. First, the documentation should describe the objective question the model is trying to address. What is the model trying to predict? Why? Second, the documentation should describe the stimuli accommodated by the model. What are the key inputs to the model that affect the model results? Third, the documentation should describe the real system the model is trying to capture. What are the key controlling processes and variables in the real system? Fourth, the documentation should describe the temporal and spatial scale the model was developed for. Does it capture processes at fine temporal scales? For example, bacterial growth occurring on scales of minutes or hours, versus climate change processes that may operate at decadal or centennial scales? Or does the model apply to a point location on a landscape, or does it describe processes that are distributed across an entire landscape or region? Fifth, the documentation should describe the equations used in the model. For the key components, variables, and relationships captured in the model, what is the underlying mathematics? Finally, the model documentation should describe how the model was evaluated. What criteria are used to determine if the model is a good model or a bad model? Generally, this relates to how well the model should be able to predict the behavior of the observed system. For some applications, an extremely precise model is required. For others, a merely good prediction may be sufficient to address a particular question. We will be discussing specific techniques for assessing model performance in later modules. So, to recap, in this module we identified several types of models and provided some criteria for when a particular modeling approach might be appropriate. In particular, we focused on empirical versus mechanistic models as a key differentiator. We also discussed a number of advantages and possible liabilities associated with a modeling effort. The advantages focused on communication, better understanding of the system behavior, an ability to predict system response, sometimes for systems that are difficult or expensive to replicate in the real world, and an ability to better design, manage, and optimize complex systems. Liabilities included time and expense, exposure to hidden assumptions, challenges to correctly operate a model, and interpreting and understanding model results, particularly for more complex models. We emphasize that it is important to understand the question you are trying to respond to, and that picking an appropriate model or modeling approach is dependent on the question being asked, as well as the system context, the degree of understanding of the system, the availability of data relating important variables in the system, and the need or not to capture variability in the system. Finally, we describe documentation required for models, emphasizing Overton's criteria as a useful construct for documenting model needs, inputs, structure, approach, and evaluation. In the next module, we will be looking at establishing relationships between variables as a prelude to developing some mathematical models.